Hello and welcome back to Superconductors for Data Centers. This is the second part where we go into detail how we designed a 100 megawatt hyperscale data center that is only run on DC, and this DC is distributed throughout the data center via a superconductive busbar system. Joined again or continued with Wolfgang Reiser and Victor Stark from Vision Electric Superconductors. Enjoy and reach out. Thank you. Okay, good. So by eliminating components, do you also think there will be an increase availability of the system?
Definitely. If you have less components, you have less failures in those components and less outages. So definitely this helps to increase the efficiency of a data center, the availability of a data center. Downtime will be less.
Yeah, perfect. So it makes sense on an operational level as well.
Yes.
Yeah, great. Okay, let's come to this. So this is actually now the single line, the stuff that we developed together, showing the concept of our specific OCP 100 megawatt EOS data center. And please, Wolfgang, walk us through the single line and also through the comparison of the AC power distribution and the superconductive DC power distribution, because you can already see in the picture this is quite a reduction.
Okay. This is the consequent concept we developed out of the ideas of Intel 15 years ago and of the experiences sampled or gathered together in the last years. So looking to the left side of that slide, you see a single line diagram of a data center. And the main part of that is that we have defined 22 what we call OCP modules in one of those rows. We have subdivided the whole data center into 3 rows, and each of these rows consists of 22 modules, and in each of those modules it is possible to house servers or storages or other IT devices with a total power of 1.5 megawatt, 1,500 kilowatt. And to supply those 1,500 kilowatt to each of those units of these OCP modules, that is very easy. If we start from a bus bar on top of that, have that horizontal bus bar, which is fed by a lot of different power supply or power sources. One part is missing, and that is maybe on top of the roof of this data center. You can also install and imagine there's solar panels, and solar panels can also be very easily connected to that. So solar panels, grid connection via rectifier units, and also generator, emergency generators can be easily connected to this horizontal collector bar and then distributed to the 6 bus bars that go to the 3 buildings, which are housing each or consisting of 22 OCP modules each. The nice part is we are here working on a voltage of the battery level. That means we do not need battery for emergency case in each of those modules, but we have moved the battery outside. there is no resistance between battery and the single OCP modules. That means there is no voltage drop in between. There is no power loss in between. So the battery works as if the battery is directly standing beneath a module or beneath a server rack. So this is also possible for emergency cases to use one common battery, and by that the total battery capacity can be reduced. If you are looking to the total supply of all three houses there in the data center.
Yeah, let me rephrase this because I think you mentioned a lot of very good points. So one obviously is that traditional DC supplies in data centers usually have a big problem because we have data halls about 200 meters long, or even a little longer, that if from the start of the hall back to the end, you would have a massive voltage drop, right? It's not easy to supply the same level over such a long length traditionally, but with superconductor bus bars you will have the identical voltage and supply stability over the whole length, correct?
Absolutely correct. Well recognized. Yeah. So that is one of the big advantages. And in most data centers, the problem is not on the supply voltage, the problem is on the ground voltage, and therefore in a lot of cases you normally have double ground wire, double ground cross section, because the ground is in most cases the critical point. And especially if on a tier 4 data center you have A and a B supply, then you have normally a potential difference between A and B, and this is not the case with superconductors. So this does not give additional problems. And I've spoken to data centers where the operators are telling me that they have year by year a failure of power supplies in the racks, and they have to exchange between 5 and 10% of the power supplies simply because they are not working correctly because of unbalanced potentials between A and B power supplies. That is possible. Not in all data centers, but sometimes it's possible.
Yeah, that is definitely an issue. I've heard that too. So I have another question, because it is here shown displayed. The 50 megawatt rectifiers, which sounds a lot, and we're talking for most people of an unheard technology, but just to assure, those technologies, those transformer rectifier units are existing for the aluminium smelter industry, right? For the big pharma, you have actually those are relatively standard items, although they are new to the data center world, correct?
Yes, but the aluminum industry, for example, as you mentioned them, they are running 24 hours, 365 days a year continuously. They allow a downtime per pot of maximum 2 hours, and they do not allow a downtime of the whole line. And therefore, I know some of the aluminum plants that are running now for more than 50 years without any downtime of the complete system. So this is, standard technology. Of course, that high efficiency or that high efficiency is reached by a lot of redundancies, and redundancy here in this case could also be a case. And of course, here we also show some redundancies. If the grid has a failure, has a blackout, then, for example, the generator units are coming up and supplying the power to the data center. Of course, high powers are in this case also creating high currents. And presently we are demonstrating a 200 kiloamp busbar system in an aluminum plant. And so, yes, it is existing and it's working well.
Perfect, because I'm sure that, having this discussion with the hyperscalers, this one will be one of the first questions: how available is the system? And I think it's important to address that early, and very good, that those industries are even more critical in terms of their availability.
Yes, of course. If there is a power outage in an aluminum industry, all the pots will freeze. That means that the complete plant will be out for more than a year. So that is really a disaster. And just on the relation of the currents, here in this case, we probably will need about 30 to 40 kiloamps and not 200. So superconductors, they can carry a lot of current on very small scale.
Perfect, thanks you. Let's go to the right picture and have a quick comparison between the different systems that are shown here. I think
Yes.
that is already you see that the lower picture, which represents the superconductor busbar system, is a lot less easier. Walk us through the different components, please.
Yeah, you see it directly. There are more components on the AC power distribution than on the DC and superconducting power distribution. You're starting, let's say, at the battery rectifier and the battery itself. So on the upper part, you have your rectifier feeding the battery, and you have a converter converting the DC voltage back to AC, because you want to transport a lot of high energy on a lower voltage level, because you want to reduce your losses. And this is the only possibility if on conventional material, that you are reducing losses by increasing the voltage and reducing the current. And such a transformation with a transformer is only possible with AC. So you have a lot of you need a lot of components to think about reduction of losses, of power losses. And this is the miraculous thing in superconductors. Superconductor is really a nice material, and you can conduct currents without any losses. And therefore you can go on a very low voltage level. And here the voltage level on the lower scheme is the voltage level of your battery. And it could be 400 volt, it could be 500, 600 volt, or whatever you like to have as a battery voltage. And therefore this voltage can be used to conduct directly to, closely to your racks. And that is very nicely, and that gives a lot of advantages. So it's not only the reduction of components and the higher availability, as I explained it earlier. It's also the reduction of power losses, and that is essential for all DC data centers. And therefore we can really go to a higher scale, to the hyperscale data centers, and we love to go there.
Yeah. So we see here there's the rectification in the beginning, the direct attached battery with the native 400, 500 volts, and then the direct supply through the bus bar with the tap-off system we show in a bit, that has the only DC-DC conversion down to the 48 volts of the OCP rack, correct?
Correct.
Yeah. So you see, so this is basically two steps or two transformation in a sense compared to the upper transformation where we have 1, 2, 3, 4, 5 only even in an OCP rack. In a traditional data center, it's 7 or 9 or even more steps, correct?
Correct, and it's here in our case it's DC to DC, and in the other case it is AC to DC, DC to AC, and then AC to DC again, and not only voltage conversion but also conversion from AC DC DC AC, so which gives additional losses.
So it's really a lot simpler and nearly lossless. Nearly lossless, yeah.
Yep.
Perfect. Okay.
And to add this, if you compare these two diagrams here, above and below, if you do not need all these conversion steps, it also means that you have the space available as white space. You can put additional servers in there, so you can just have a higher output on the same space.
Yeah, but go to the next slide and then you will see that.
Perfect.
Yes, okay.
Perfect, Victor.
Yeah.
You want to explain what we see here?
Yes. I already said that you can put more servers on the space. That's the one thing. The other thing, if you think it from the beginning to the end, it also means that you have one line from power generation to the rack. And this also means that if you have a tap-off box with only DC conversion step, where you can feed all the servers, you do not need the power shelves within the servers. You can also replace the power shelves and put servers in there directly. And this is also a huge advantage. I mean, you have normally 2 or 3 power shelves in this case, and that means just a 30% higher rack density.
Absolutely, I think that's the very exciting discovery we made when we were discussing this, that OCP has nearly the perfect prerequisites for the superconductive busbar, because there is already a DC supply throughout the rack, and we easily can integrate this technology in an existing rack technology.
Yeah. So
let's go over to the busbar, please, to the structure of the busbar, because that is, I think, something for most people who have not seen how this is actually working.
Yes, exactly. That's that's always the question. I mean, if you look to such a single line diagram or something, how would the superconducting busbar looks like? The picture on the right side here is a superconducting busbar. That's our system. We call it IceBar. And this is the system that we installed in the chlorine plant that we mentioned before. So as you can see, that's a module. You can realize bending radii as you need them. It is a double-walled steel cryostat with vacuum between the two walls for isolation reasons. And in there you have the superconductor tapes or the stacks. And what you also can see is a pressure valve here. So you have to move the liquid nitrogen, which is inside the system, And with this valve, for example, you can regulate the overpressure if this should occur, which is not normally not given, but it's just a security feature. And this brought us also to the idea to use the liquid nitrogen for cooling down peak temperatures. And we can also use the busbar system for firefighting purposes. So there are a lot of additional value, additional applications that can be covered, and not only the transport of the electricity.
You raise a very good point, because I think that was an exciting discovery, that, you know, with basically introducing liquid nitrogen to a data center, this can easily be multi-purpose, and integrating the busbar correctly in an ideal way, you can create a more efficient cooling solution and cost effective, and you also have already the tools for firefighting already included in your electric busbar, right? So combining those components, this is really an exciting new way on how to think about data centers.
Yes, and that's why I like our EOS concept, because it just puts together so much innovative stuff in one concept. I love it.
So what is, so to explain me, because we see here, I think one important step, you know, we see on the left side close to the rack, we see the cryostat, and also a tap-off system, a cooling tap-off system. So what is needed to go from, you know, the superconducting temps, as we heard, 77 Kelvin, about 200 degrees, minus 200 degrees Celsius. What is necessary to go to regular temp?
So the tap-off box is, you can also say that it is a current lead. So what you see on the picture here you mentioned is a current lead, which...
May I explain it a little bit later on the next slide?
Yeah, sure. Okay, sure.
But I want to come back on the situation that we are running with liquid nitrogen. If we just evaporate liquid nitrogen, it has two effects. First of all, it is reducing the oxygen content in the normal ambient air. And second, it's cooling down the air. So both effects are helping to run or to prevent data centers on shutting off on peak situations. For example, if it's only for a few days a year too hot in the data center, then only for these 2 or 3 days per year, you could use additional liquid nitrogen vaporization just to bring down the temperature of the servers. And if, for example, if you want to be sure that no fire is coming up, yes, you continuously evaporate a little bit of liquid nitrogen to bring down the oxygen content to a level of below the normal one, which is around 16 or 17%, and which prevents then from taking a fire, starting a fire. So these two advantages are there if you're using the liquid nitrogen. And if you go to the next page, I show you how liquid nitrogen is created or is stored.
Perfect, thanks.
Yeah, you see on the left side, you see a tank, and you see a small vessel, a cut off a small vessel. And this is normally a vessel where the temperature of the liquid nitrogen is subcooled, because because for the operating temperature of superconductors, it's better to have around 70 Kelvin than for 77. So we are cooling it a little bit down, which also is good for evaporation energy if we need that. So out of that vessel, we can feed a lot of liquid nitrogen in emergency cases if for firefighting or for peak temperature shaving, if that is necessary on only a few days a year. But we are also using that equipment to cool or to prepare the operating temperature of the superconductors. So this is a relatively simple equipment, and the supply of liquid nitrogen is also relatively easy and simple, and is not very high in costs. The break-even point between supplying or having cooling power with liquid nitrogen and the other possibility is, instead of that, using cooling machines, is at about 0.1 about 10 cents per kilowatt hour on energy costs. That means if your energy cost on a data center is higher, then definitely liquid nitrogen supply is much more efficient.
And as you explained me, that liquid nitrogen is basically a waste product and relatively cost effective, right?
Yes, liquid nitrogen is basically coming out of the oxygen and oxygen production, and oxygen is used in all steelworks, in all hospitals, in a lot of other facilities. So in laboratories, and and therefore this is a byproduct, because more than 3/4 of our atmosphere is just liquid nitrogen, and therefore this is just produced by extracting oxygen. So therefore costs are mainly coming from transport and not from the production of liquid nitrogen. Liquid nitrogen is available.
Perfect. So, and as you said, the transport, so this is just a medium you ship, just like your diesel tanks, right? You have like a supply infrastructure over the road with tank trucks, correct?
Yes, yes. And if you look to that tank, normally that is a tank which contains a mass of liquid nitrogen which is needed in 1 or 2 weeks. And this normally it's a full automated process. If the tank level is falling below a certain level, a signal is going to the supplier, and the supplier will automatically come next day with a tank lorry and refill the tank. So that is just normal standard within industry.
Perfect. Thanks. I think this
if you look to the right place, there you see those tap-off units, and those tap-off units taking off the power that is in this superconducting busbar. The superconducting busbar itself looks like a pipe system, and you only see from outside that it's a pipe and you can touch it. There is nothing special with that pipe, but it contains all the superconductors necessary to supply the OCP racks. And on the blue cases you see on these tap-off boxes, these tap-off boxes contain actually 3 different functions. The first function is something we call the interface between superconductor and copper. It's called a current lead, and that is just the tap off from the superconducting system and going to ambient system, making, let's say, ambient temperature current out of low temperature current. It's just a interface.
So it's relatively easy.
That is really easy. That is just really easy. We exactly know how to do that. And it's small, absolutely small, for relatively small current. And then we have a DC converter, which is very efficient because we only convert DC to DC, and we convert 500 volt, for example, or any other voltage which is coming out of the battery. We convert to 48 volt DC or any voltage which is required on the OCP rack, or we convert to 24 volt or whatever. So that is something which is very, very easy to do, and which is very efficient in the process itself. And of course, you need some protection device to be sure that nothing happens if a short circuit on the OCP rack happens, that will not destroy or will not damage the busbar system. So there's a protection device on it. And we also have a monitoring interface going to the central operating unit of the data center to always show the operator, the system operator, about the situation of each of the OCP racks.
So there is the system. Your system comes with an included monitoring for the actual power supply. So you see exactly what's happening in your data center in terms of energy.
Yes, because we have to integrate sensors that measure voltage and current for the controlling of the DC converters, and that information is available, and why not using it for another purpose? So it's something like integrated smart technology. It's just a smart chip that is then used to create an interface and to bring it to the central control room.
Perfect. Okay. So that I think is a very, very good explanation. I think we covered all systems, necessary for the cooling, for the distribution down to the rack, for the single line, for the rectification. That is a ton of information, and we know each other now for 6 years, and I'm slowly beginning to integrate it and grasp all the necessary concepts. So I think the industry will also maybe take some time, and this is a good first step to really demonstrate all those things. I think we have another slide summing up a lot of the advantages where we talked about, correct?
Yes. That's on the next slide. Yeah. So we
can see it.
Yeah, we can see it.
Oh yeah. Perfect.
So I think I will not repeat all the advantages. I think we can also that is something which can be read by everybody that is looking to our presentation here, but it's definitely the size of the complete system. The system is very compact. It's modular. So if for a data center you have a reuse or you have to change something on cable systems, you have to recable everything. Here you just have to open one of the modules and you can add another module. You can change directions. You can change all applications here on the modules. We have a very, very high energy efficiency and a very low carbon footprint, because it's not only energy efficient, it is also material efficient. you can easily see. So that is good for the environment. We have no thermal emissions, and after the lifetime of the system, we easily can separate the different materials, and we are only using straight materials and not compound materials. So the materials can be easily separated and recycled. And of course, we are taking care of security. The complete system is completely encapsulated, so very high protection degree of IP68, and therefore it is human safe and absolutely safe for everybody that is working in a data center. So of course, a lot of other side advantages are there.
Perfect. You mentioned, we talked about a lot of those advantages. So, what are there some disadvantages that you consider?
Yes, of course. That is always the question. Why is it not yet installed in all data centers? Yes, there are some hurdles to go over. First of all, as I said, we are looking for a hyperscale data center. Why is that? Because we have a base equipment, which is the cooling system, and that base equipment just adds in the beginning some investment costs, so which are paid back later on. So we like for the cooling, we like higher powers, because the efforts for cooling is not proportional to the power of the data center, but we have a strong base investment to carry, and then a very small upgrading with the power of the data center. So we like 40 MV better than 20 MV, and we like 100 MV better than 50 MV, which is then giving more advantage for the total, let's say, cost situation of a data center. So therefore, we are looking for hyperscale data centers. And why is it not installed? For the installation, the complete system, power system, needs to be redesigned. As you saw on the previous slides, the complete power system starts at the beginning at the power source, and if you do not redesign it, you will not take the advantages for superconductors. So what happens if an order for a data center is coming out, and if an electrical company is receiving that order, it is always mission critical. That means it has to be installed in the most compressed time possible. What do those companies do? They have their previous old data center in the drawers. They take out the old specifications, the old designs from the drawer. They change a few figures, and they purchase, or they give the purchase order for the material out. And that is always the critical path they have to follow. And so they do not have the time to redesign the complete power system. So, and what is, if they have no orders? If they have no orders, they do not have a real data center to design. And if you have no real data center, you do not spend the time for the redesign of the complete power supply. So that is a situation we are in, and therefore we are looking for pioneers that can give 6 to 12 months of additional engineering and restructure time, and we are only looking for hyperscale data centers. So we are a little bit stuck in that situation. We have a very good proposal. That proposal have been, or that design had been approved and demonstrated by around 20 data centers worldwide. It is a IEEE study and other studies that prove that DC data centers have a lot of advantage in the reduction of carbon footprint, in the reduction of losses, in creating higher efficiencies. But nobody is giving us the time to demonstrate, to prove that on a real data center.
I think you make a good point here, because with all the discussions going on, also including in the OCP, that more design choices have to be long term, and so looking at all the advantages and also see a bit of the return of the invest, I believe that with all the advantages you presented here, it makes absolutely sense to look into this, since it's uncovering one of the biggest losses still existing in the data centers, and it enables completely new designs that are way more effective and efficient in terms of space, structure, integration of renewables, and has also the absolute availability footprint a hyperscaler would need, right? So
absolutely. I'm absolutely sure if the first one started with that concept, all the others will follow, because this would set a benchmark on efficiency on data centers.
Perfect. That's I think that should be the goal, the new efficiency standard for data center electrical supply. Okay.
Absolutely.
Okay, so then you were highlighting that there is an initial cost to this. So let's look at some of those returns and those numbers.
Okay, that is now the time for Victor, because he is the sales and marketing guy.
Yeah. So what you can see here is. We talked about higher capex, lower opex. What does it really mean? We made a study on that because we wanted to know for ourselves how expensive all this will be, how much money can you save on a data center, on a hyperscaler, if you use superconductors. And therefore, we also bought some studies, and we also engaged a consulting company to help us getting through all the figures. And the figure here below are the cumulative net savings of using a direct current data center together with superconductors. And we compared it against a normal data center like it is everywhere. And what you can see here is that the higher the power consumption of the data center, the more beneficial superconductors are here. So, for example, we take the 80 megawatt data center here. You will have a positive cash flow here in the second year, which if you sum it up for a 10 years period, so if you really look for 10 years operation of this data center, it would mean that you save 43 million within this 10 years in euro. Compared or given German electricity prices. We can also make a calculation on the local prices and with other things. But I mean, that's a huge number. It's like 50 million in 10 years, like 5 million a year. It's a lot of money, and this is something that you will have in addition to all the other benefits that has been explained here.
Perfect. So that is that obviously you mentioned it depends a bit on the energy price, but still the reduction of components and the availability benefits, and also the affected components like the fire protective system and the climate system, which is usually one of the most expensive part in a data center. Those are all affected, and we probably might be as an afterthought have to look into all those design benefits that we create, right? Which are not even addressed here.
Yes, correctly. They are not even addressed here. We do not calculate the dimensioning of the cooling system and so on. So those side effects would bring another value to the whole concept.
Great. So you mentioned other operational benefits. Do you have any further, or are we? I think that's pretty much it, right? It shows clearly, your numbers show clearly that the reason why Wolfgang would like to speak to hyperscalers is you need a big data center to make this interesting quickly, right?
Yeah, there's one point I'd like to point out here. It's the Scope 3 emissions. So if I talk to data center people and what goes around in that business, I more and more often hear we have to reduce the Scope 3 emissions. First, I had to look what does it mean? What are Scope 3 emissions? So we are talking about the emissions that a product has from the production until the recycling. So we take the whole life cycle of a product, and then we try to measure the CO2 emissions on that. And many data centers would like to reduce this Scope 3 emissions. And superconductors are the perfect fit for that, because you don't have cables which are difficult to recycle. You don't have that much material that is needed to build the system. And you can reuse these modules. So IceBar is a modular system. If you say after 10 years, okay, I'd like to build another data center, you just can reuse these modules. They do not break somehow or something. And even if to one module, if there happens something, you can just change this one module, and you do not need to put a whole cable through the whole data center or something like this.
Perfect. Great. Okay. I think that covers this quite extensively. Yeah. I'll leave it to the final words to Wolfgang and Victor. And I'm excited to present this in live at the OCP Summit in November together with Victor in San Jose. So happy for some final words. Yeah.
Victor, you start.
Well, the last words I said, that already was my my last words indeed. But I'm also very curious and very excited what will happen on the OCP Summit, and I'm very eager to present this together with Karl, and just to see the reception and of the people there, and what will happen there.
Okay, I'm absolutely convinced that this concept will bring a lot of advantages to data centers and will be the next step in the efficiency road of data centers. Data centers made a lot of efforts to increase their efficiencies in the past, this year will give an extra large step into the right direction to zero emission. So, Karl, thank you for organizing, and I hope we will get in a good contact with one of the hyperscale operators.
Thanks so much. I think this is really exciting, and happy to continue to work together on this.